Yeah, so good morning, everyone. So I will be discussing on the compliance monitoring using Synchrophasor technology, how we are using it for, because, means in grid, multiple components are getting connected and already connected, and they are getting connected on day-to-day basis. So, and these, means when we talk about this equipment, they have to follow certain standard, and they have to provide, the adequate support to the system also. So thus a lot of compliance requirements are there for the different equipments. And during the operation also, there is a lot of compliance in regard to the various standard that is being followed in the power system. So today we will discuss how we can utilize this Synchrophasor technology for monitoring of the compliance in the power system. So just a brief overview. I think many of you already know about this. What are the data that are available from the Synchrophasor devices, the phasor measurement units? So the first is the analog data, that is the voltage and current phasor. You will be able to get the magnitude of the voltage as well as the angle, which will be basically relative to the, means the GPS signal basically. So based on the relative angle that you get from the GPS signal, you can calculate the phase angle separation between the two nodes by calculating the difference between these angles, voltage angles. And this voltage, the whatever the difference that you get, basically these are what we call as a power angle in the power system. Then what we get is the positive sequence component of the voltage and current phasor, because this positive sequence component, basically these are being utilized for the frequency and rate of change of frequency calculation in through the synchrophasor algorithm. Then we have digital status also, like protection, circuit breaker, isolator, whatever digital protection that you means digital status that you want to get from the PMU, that you can incorporate and couple it with the Synchrophasor devices basically installed in the field. And then you can have some calculated data like active, reactive, and total power and the power factor. So basically what you get from the PMU is a sub-second level dynamic monitoring of the wide area system, basically wide area power system, you should say, or the wide entire power system, depending upon where you have placed your PMU. So how the coverage is there, based on that you get the dynamic monitoring of the power system. It may be a small area wherever your PMUs are there. It can be a complete grid also where you have placed a lot number of PMUs. So you get a complete overview of the dynamic monitoring. These are some of the data from PMU. Just you can see that what I put it here. Let me just yeah. This is voltage angle, then current magnitude. You can see the fault that has happened in the grid in one of the transmission line. You can see the frequency. You can see the how fine you can get the frequency plots. You get it can be used for multiple uses like inertia, rate of change of frequency calculations. And based on that, you can get some numbers like power numbers, from which you can calculate how much is the draw, how much is the loss of generation, estimated loss of generation in the system is there. And apart from that, you can also estimate the based on this frequency drop, how the generators basically, how whether they are providing the proper support, primary governor support, or primary frequency support to the system or not. So these helps a lot in various compliance monitoring. Then you have voltage magnitude, because you can see that the auto recloser in the power system transmission line is happening, and this also provide a compliance, means a one time of in compliance monitoring for the protection system, whether the protection has operated correctly or not. Then you have the active power, and through which you can means you get a lot of information from this active power also, how the power system, whether there is a power swing, whether the power swing is properly damped or it is not properly damped. Then you can see rate of change of frequency. There are different protection schemes that are enabled on the rate of change of frequency. So how during any event, how whether the rate of change of frequency were within the limits or not. So these are some of the input, and you can see these means a good quantity of dynamic information of the power system gets available to the system operator through these Synchrophasor devices. So what can we have from the PMUs? So one thing is that you have a global time synchronized overview of large power system. So because all the devices are time synced with the GPS, and whatever the data you are getting is getting the all means from different nodes, you are getting the same amount, same data for particular time stamp. Okay, so you get let us say there are nodes which are wide apart by 1,000 kilometers. So you get the voltage of that node and the relative angle of that node, as well as the another which is 1,000 kilometer apart, at the control center at the same time. And you can use these to get a complete picture of a snapshot of the entire power system, and you can just play it because all at each small time interval these data will get updated, so you get a very good fine refined dynamic overview of the system. So then the because why this dynamic fine resolution is important, this how much data is reporting to the control center at each second. This is very important in the sense that because we wanted to view the dynamic phenomena. In generally what we term about the dynamic phenomena is that whatever is occurring, means the governor, how the governor and how the various controls which are electromechanical in nature, and those how they are means impacting the system. Let us say if you talk about a fault is happening in the system, it occurs within the millisecond of, means it will keep on for 60 to 70 or 100 millisecond approximately. And you are able to capture these kind of dynamics, and the subsequent to that there will be, means electromagnetic transient in the system, and sorry, electromechanical oscillation in the system, not the electromagnetic transient, because PMU will not be able to capture the electromagnetic phenomena. It will be able to capture the electromechanical phenomena in the system, like oscillation, power swing, and all these activities. Okay, then that's why you means if you have a very good reporting rate from the synchrophasor devices or PMUs, you get a very good overview of the dynamic phenomena of the entire power system. Like the active and reactive power, you get the transient, a small signal stability overview of the power system, like power swing and oscillation. From the frequency and rate of change of frequency, you get the frequency stability phenomena. We will look into these compliance later on in our slides. So, and there may be further, means further applications are being developed, so we will see in the course of time lot of things are happening in this direction. So overall it is helping in the reliability improvement, situational awareness, and post dispatch analysis for the grid operators. So just a brief overview. I mean, so what is the difference between the conventional system, conventional SCADA system, through which is the eye of the any system operator or any grid operator, how he looks at the grid, and another side is PMU based, as means wide area monitoring system. So the conventional monitoring system that is based on the SCADA, it is basically uh, conventional monitoring system, basically, which is based on the remote terminal units, basically the SCADA system that we call. It has a slow sampling rate. It is not time synchronized, means asynchronous in nature. You can't monitor directly the phase angle through that. And the error in the, means whatever the quantity that you are measuring, it can be, it is less than 2%. And as it is being utilized from since a long time, this conventional system is there, so its coverage is very high. You can go to from a very EHV level to the LV level also. These kind of coverage is available with the RTU based SCADA system. While the PMU, means from 2003 blackout in the USA, it has started, means more utilization has been discovered, and more emphasis has been given on the implementation side. So the PMU has a fast sampling rate. It is time synchronized. Whatever the limitation that you are getting in the RTU side, directly you can monitor the phase angle difference between the two nodes, and you can measure the dynamic, means the states of the power system basically, and error is also less. And earlier it was a limited coverage, but with the, means amount, means the amount of information that the system operators were getting, and the usage, the improvement in the usage of these synchrophasor devices, the limited coverage is not a limitation anymore. Many of the utilities are going for a very wide coverage. Okay, so just one thing, let me just share this one. Yeah. Yeah, this one is just one example of how this is the PMU. The one particular node is there. Okay, and you can see the voltage of that node and the active power of the one particular transmission line. You get, these are the same thing that is being monitored from a SCADA. Below is the SCADA PMU and the voltage, the active power and voltage, and upper one is the what you get from the PMUs basically. So you can see that the dynamics that are happening in the system, in the electromechanical range, which is basically what we call, it ranges from 0.01 hertz and it goes up to 3 to 4 hertz basically, in which the like the excitation system response, governor response is there. Then there are other devices. The overall system is responding to some events. So this is how, means these information are basically, you get this dynamic overview of the system from the PMU devices. So you can see that this is one of the plot that I've taken from one of the NASP videos. Basically, they have shared these in the NASP means website. So you can see that you are, this is one kind of oscillation of post, you can see then one fault is there, a fault get cleared, and then subsequent transients or swings, power swings are there. Okay, so you can see the SCADA is not able to capture, it is able to capture this kind of difference, but it is, means, but it is not able to capture the complete dynamics of the electro, I mean, whatever the dynamic event that is happening, it is not able to capture those. So this is the benefit that you get from the synchrophasor devices, just to give an overview to you. So, how in India this initiative has taken place? So, in India, the synchrophasor were adopted in means it was adopted in 2010, and we started with a single pilot project in the northern part. Then all India, means each region has taken a pilot project, and then these pilot projects got integrated at the with the central NLDC level, and we have a, means, the 60 PMU from different vendors were integrated at the national level. So this was a one kind of unique experience. So we are trying to look into the aspect that how it can be utilized for real time operation, like fault detection, localization, oscillation monitoring, angular stability monitoring, and synchronizing the two large power system, which has happened in 2013 with the integration of the this particular portion of the grid with the southern grid, actually. So this was also one of the unique use case of utilization of the synchrophasor in real time for synchronization and islanding of the large power system. So means various reports has been published by the operators, which are mentioned here, and based on that there was a view that okay, we need to go for a larger scale deployment. So based on these, the unified real time dynamic state measurement system project has come into the Indian power system. And here you can see that earlier we have 2000 pilot project around 60 PMUs. In 2018, URTDSM project, basically 1,402 PMUs were installed all over India. And in that, further, it has been enhanced to more than 1,700 PMU right now, reporting in the Indian power system. They are installed in the Indian power system and reporting to the control center. So this is how, means, we have moved from a smaller scale project to a larger scale by first identifying the benefits and then moving into the larger direction, larger implementation, so that we get a complete overview how we can enhance our system operation activities from based on these synchrophasor devices. So just an overview how this many number of PMUs are, means spread. You can see the geographical spread across all India. So this is how a typical control center, the outlook is there. So, I mean, this is the conventional SCADA system, forecasting, reserves, and all these are there. And this is the synchrophasor system that is also available to the control system operators. So they get a complete overview from the one side. Conventional SCADA is already there, and it is being used for a steady state or the quasi steady state monitoring. Another side, the dynamic state monitoring is being done by this synchrophasor system. So let us come back to the topic on the compliance monitoring, basically. So prior to going to the means first this application on the compliance monitoring part, the compliance in the power system, basically you have certain rules and standards based on which devices have been implemented in the system. They have to follow these standards. Their capabilities are based on whatever the guidelines and rules that has been set out. So, and there is the Indian electricity grid code is there, state has their own grid codes. So all these whatever the equipments are installed, they have to follow these I mean standard and rules, and whatever has been prescribed, that the limits on the voltage side, limits on the transient, limit on the fault clearing side, what are the limits on the means damping, what are all these means have been laid out in the standards. On along with that, the how the system should respond during any kind of contingency, all these are there. And for that, some adequate mechanisms are also there, so that their response should be in such a way that it should support the reliability of improve the reliability of the entire power system. Okay, so based on these, the first kind of compliance that we are looking at, the primary frequency response. Whenever there is a fall, the generation tripping in the system, there will be a fall in the frequency, right? Because electrical power suddenly get reduced. Basically the loss, we basically lost a unit. So we basically lost the mechanical input as well as the electrical whatever input was there. Electrical output is the same. So that's why all the generators start slowing down. So that's why we see a fall in the frequency because of that. So when there is a fall in the frequency, this is what we call as a means there should be a first impact of the inertia should be there, which will be followed by the frequency, first stage of frequency control, which we call as a primary frequency response. Now it is also with the new Indian electricity grid code, it is known as primary response ancillary services, PRAS. So this has to be provided by the generating unit basically right now, and the generating unit should provide it through the governor response. And there are loads, rotating loads are also there. They also provide the load damping in the system, because the motors, speed of the motors is proportional to the system frequency, the induction motors. And with the reduction in the frequency, the motor load, also the p quantum of the whatever they are going to take the active power from the system, also reduces with the frequency. So it's a self-regulating mechanism for the loads, while the generator has to provide by sensing the change in the system frequency and adjust their mechanical input to change the electrical power output. So let us say if any generator is has to provide the response, what it will do is that it will provide the primary response by using the excess steam that is already there in there, on the govern this prior to the valve, the governor valve. And by opening of the valve, the steam are suddenly put into the system, so that suddenly the active power generation can be increased from that particular unit which is providing the response. So this primary frequency control, it is a mandatory and automatic. It is not, it is not driven by any external centralized system. All generator has to comply with it. There has to be a primary frequency control in all the generators. So their governor has to respond for the any drop in the frequencies there. They have to provide the response. So how you will see those, how you will monitor those, because these, if you see this plot basically, so what you are able to see is that the frequency drop, it is like 0 to 10 second, it is up to this, you can see the fall in the frequencies there. So this is being stopped by the governor response as well as the inertia in the system, and then it is start recovering back. So the primary frequency response kicks into the system within 5 to 6 seconds, and then the system frequency come to a nadir frequency, which is the lowest frequency for that event. And then it starts going up with the increase in the mechanical input from the different generator spread in the grid. All are providing the primary response. Okay, so there are criteria who will be providing the primary response. Let us not go into that, but think in the direction that all the large generating units, hydro units, also all these have to provide the primary response, or the gas turbine units, all they have to provide the primary response into the system. So when they provide primary response in the system, then there is they add electrical energy into the system. That's why the frequency start recovering back. So you can see that the time domain, that it is within 10 seconds, this has to kick in. And then you can say that within the 20 to 35 seconds, something like that, you can see that up to 50 seconds they are responding, and it is there. Means primary response control is there up to 4 to 5 minutes. So they are providing the response from this side to this side, means this domain. So from ranging from seconds to some minutes, basically, the primary response will be there from these units. So if you try to monitor through a SCADA, you do means this drop in frequency. If you try to monitor, then drop in frequency will not be like, means you are able to monitor at each 1 second level. Okay, from the SCADA system. So the drop in frequency, we will not see such kind of a smooth plot. There will be drop in frequency. Suddenly you see that, okay, frequency is reducing at some due to some events, basically. While the PMU provides a very fine resolution scope of the system, because means electromechanical dynamics, when the governor is happening, trying to provide the response, you need to see the how the entire power plant is providing the response, whether the response is proper or not, justified or not. So what are the ways in which you can monitor this kind of response? So one of the things that I will just show you, this is one, yeah, various generating complexes are there, and on their outgoing lines PMUs have been placed. Okay, so whatever the generation is there in this plant by all these 3 units or 2 units, those can be directly monitor how much the active energy they are supplying into the system. That can be monitored by these from the, if we have PMU, then summation of the active power of these 2 lines will correspond to the whatever the active power is being generated collectively by these 3 units. Okay, or the all these whatever the means configuration is there of the unit configuration at the plant. So if you have the PMUs at the outgoing line, then it is very helpful for monitoring the primary response. So let us say if this plant first is then generation B. So you can see generation B has, two outgoing lines to this substation and two outgoing to this substation with two units are there. And if you have the PMUs this is at the generating plant, the PMUs are there on the outgoing line. So submitting all these PMU will provide you the net how the active power is responding to the drop in frequency. So you can see the frequency is dropping and you can see the active power of the generation suddenly increasing, and it is providing a response and it is sustaining. So it's a very good, response is adequate in nature, and you can see that yeah, response is adequate in nature, and you can see that it is sustaining also, and it has provided a immediate response just post event. So this is what provides a confidence to the operator that okay, this particular unit is providing the response as required by the various standard and the grid code. While if you see this particular generating unit A, so initially it has provided the response. You can see this, the plot is there. So this blue one is the frequency and the red one is basically the generation, complete whatever the generation input from that particular plant monitored through these PMUs. So when you see that there is a fall in frequency, it is providing the response, but it is withdrawing the response immediately. And after a lot of delay, they are again starting to respond. So this is a kind of delayed kind of response. Okay. So this is also telling me that okay, there is a requirement of tuning of the governor performance at this particular plant. The third one is you can see that it has provided an immediate response and it has withdrawn, and then thereafter no response. So we call it as a poor response from this particular plant is observed. So this is what we are observing through how we can monitor the primary frequency response from the units, and we provide a feedback to the units whether their response is adequate or not adequate, whether there is a issue, delayed response is there, or whether the response is not proper, how this can be improved, all these, and how these if there is a non-compliance is there, we are reporting it to them so that they can take corrective action to improve the primary frequency response. Then the second is the power system stabilizer tuning. Okay, so in the power system is basically a coupling between the means electrical system and the mechanical system through the rotor and the stator from the of any generating unit. It's a coupling of multiple generating plants are coupled through that. So there is an electrical part on the grid side, electrical side, and there is a mechanical input that is coming from the turbine side, right? So these electrical and mechanical input, this system is coupled through the magnetic force basically between the rotor and a stator magnetic field. So certainly when there is a transient in the system is there, these will have some oscillatory phenomena, and these oscillatory phenomena we call it as a low frequency oscillations. So basically whenever there is a disturbance is there, power system try to reach the new equilibrium point. While trying to reach the new equilibrium point, you will have certain kind of power swing, oscillation, all these will be there. So these low frequency or the electromechanical oscillation in power system, these are in the range up to the 5 hertz. And you already have I thought that the classes would have already, means earlier classes would have already told you that the PMU is providing me a sample, it means reporting rate of PMU is 25 hertz per, means you are getting 25 samples per second. So as per the Nyquist criteria, will be getting around 12.5 hertz oscillation you can monitor. But means if you go on to the better accuracy side, then what we have observed is that rather than 12.5, just around 6 to 7 hertz, you will be getting a very good frequency, means detection of the oscillation in that range basically. So that this Synchrophasor has provided a very good capability of to the system operator in monitoring these oscillation, which earlier were not means exactly captured through the SCADA system. So these remains, means whenever there were tippings due to the oscillation, these remains means until unless you have better recording instrument available at the substation which can record all these oscillation, you will not be able to, the system operator will not able to analyze these kind of events. But with the PMUs with the 25 hertz reporting rate, you are able to now monitor this oscillation in real time. And when you monitor the oscillation, not only the monitoring is important, what corrective action is required for damping of this oscillation is very important. So the one of the most effective measure to damp oscillation is power system stabilizer. Basically, it's a part of the power oscillation damping control in the system. The one side is each of the generator has power system stabilizer coupled with their excitation system. Another side is that there are reactive means active and reactive power control in the HVDC and fax devices, where you can also utilize the power oscillation damping control. So there are PODs and there are PSS. So PSS is available at each of the generating units. It is an inherent control that is available with you. So in that case, this tuning of this stabilizer, power system stabilizer, helps in damping the oscillation. So what the most important thing is, you need a very proper tuning, and you need to monitor this tuning. You need to establish the fact whether the tuning is proper or not. So what the benefit of synchrophasor data during the PSS tuning is that you already know that when you are going to go for a tuning, basically PSS tuning, you need to do certain tests, like if the PSS, the stabilizer is in service, or is when it is out of service, how the system responds to different kind of variation in the means the electrical quantities in the system. Okay, so let us say you provide a change in the V reference step to the excitation system, and you check whether the PSS is able to damp the oscillations post this with the change in the V reference. If there is a means there is a tripping of one of the outgoing lines, you do a disturbance kind of test. Then in that case, or you do a kind means you change the step input directly by tripping a reactor. So you check that how the whether the system is performing with oscillation, with PSS in service and without PSS in service for that particular generating plant. So these kind of test we do, you means monitoring of this test. And this PSS tuning is also a mandatory process as per the standards. Okay, so all the generating units above certain 100 megawatt capacity has to have their PSS properly tuned. And when they are doing this tuning and they are doing some certain test to validate the tuning, then during that we utilize the PMU to check whether the damping is proper or not, whether the PSS is effective or not. Because means PSS, if properly tuned, helps the system. If improperly tuned, it can means to accentuate the oscillation. Okay, so there are both sides. If you don't properly tune it with the proper study and mechanism involved and the proper process, then you can rather than damping, you can excite the oscillation also. So it is very important for the means system operator or the planners, that wherever this tuning is being done, it has to be properly monitored, it has to properly cross verified that it is able to damp the oscillation. So let us look into that. This is just I have put one plot just to show you that yeah, this is the oscillation, means there was oscillation has come into the system. So you can just, yeah, just let me, yeah, this is some oscillatory response. Some oscillation has appeared at one of the power plants. You can see this is the damping is going down, oscillation frequency is coming up, and this is the damping monitoring chart. So you get multiple alarms in the real times, and you get mode shape of this particular frequency where, and you can, based on the mode shape, by large, if it is a local kind of oscillation, you will be able to find the source of the oscillation. Until unless it is something like force kind of oscillation or inter-area oscillation, in that case it's difficult to find the correct source without proper tool. But for the local oscillation, you will be able to find through the mode shape itself. So this is just one oscillation has happened. You can see that the mode has shifted from this side, from the means from this side to the higher damping to the lower damping has reduced. The mode frequency is like this one. So these are the real time monitoring tools for the oscillation available to the system operator. Just a use case for you. So you can see that at one of the plants, you can see that there was PSS was out, means tuned, but it was response was not satisfactory, it was not properly tuned. So in that case, what we observe is that during the fault, we observed a, like it's a 1000 megawatt plant. So observed a 292 megawatt peak to peak oscillation, which was damping in 30 seconds. So immediately went to the plant and informed them that, okay, this is the issue that we are observing, that PSS is not providing adequate damping basically. So then they go for the retuning of the PSS, because means power plants, when the system is under development, constant network upgradation is going on, new transmission line are being, new units are integrated. So when these things are happening, the fault level, network configuration, all these are changing for that particular plant. So with those, the tuning, the local oscillatory modes, whatever the interplant mode is there, inter-area modes, these also change. So for that, you need to retune your PSS. So if that is not done, then whatever you have done in the past may not be able to provide a good damping for the upgraded network or the updated or the whatever the addition of the network. For that, the change in the system, there will be a change in the network configuration. All these are there. So for that, PSS, whatever the PSS that has been tuned for that particular plant during the kind of event, it may not be providing you an adequate response. So you need to do the retuning of your PSS, and when there is a network change also. Okay, so major network change is there, you go for a retuning of your power system stabilizer in that particular plant. So this input was given to the plant, and the plant again has went for this basically retuning of their power system stabilizer, and you got the similar kind of one event happened, and in that the peak to peak oscillation has also reduced, and the damping was achieved within 4 to 4.5 seconds. And these are getting monitored through the synchrophasor devices itself, okay, PMU data itself, okay, because in a SCADA you will not find these kind of things, these kind of details. And as we have the PMUs on most of the generating plant, so through the either the plant lines itself or the remote end of the power plant on those lines. So if we summate all those, we can get the entire power plant, what we did for the, means what, because we are trying to observe how the plant is completely responding. That power system stabilizer basically helps in damping of the oscillation through the excitation control. It is a supplementary control available with the excitation of the units. Okay, so as you know, I already informed you that the each of the power plants outgoing lines are being monitored through the synchrophasor. So their active power I am able to monitor how much the active power generation they are injecting into the system. So if you do any kind of test at that plant, so whatever the transient or variation in the active power will be there, it will be easily captured through the PMU devices, right? And the oscillation is a electromechanical phenomena in general right now, but I will not say that it's the only oscillation can be electromechanical. It can be, if you go to the classification of the stability, you will see there is a resonance kind of oscillation also. There are certain aspect on the, means this converter driven stability based oscillations also, and there are electro means rotor angle stability based oscillation also. Here we are talking about rotor angle based, okay, so electromechanical in nature. So these are in range of, I informed you that these are basically lying in the range of 0.01 hertz, that is from the governor side. Lower the frequency, slower will be the response. So that is the governor response, 0.01 hertz. Those kind of range to 4 to 5 hertz range, which can be from basically the electromechanical part covers 0.2 hertz or 0.1 hertz, and it can cover up to 3 hertz basically. So if you have a reporting rate of PMU from 25 hertz, you are easily able to capture such oscillation. So you are able to capture oscillation, and then we can use the stabilizer to see whether the plant, means we can use the PMU data to see whether the plant is responding properly. It is able to damp any kind the oscillation post any event or not. So you can see that in this plant, the PSS was tuned, but there was a lot of network change. The PSS was tuned long back, and lot many network upgradation has happened near to that plant. So due to that, the PSS was not that much effective because it has come the fault level, network connectivity, how the system is means the overall the frequency in the system of low inter area oscillation, local mode oscillation, all this has changed basically. So due to that, the PSS was not providing the adequate support to the adequate through the excitation were not able to damp the oscillation. So after this event, we analyzed for one event, the oscillation was very severe. For a 1000 megawatt plant, it was oscillating with a peak to peak oscillation of around 292 megawatt, around roughly 300 megawatt. And the damping was in 30 seconds. So if you go for the tuning, the proper after this feedback was given to plant, they went for retuning. And then subsequently for another event, we see that the oscillation peak magnitude has also reduced significantly, and the damping is within 4 to 5 seconds. So this provided a good thing that okay, the means there are field tests already in the system already has been means field test has already been carried out, and during an event also we are able to verify that okay, the oscillation is good. I mean, my oscillation damping is now very good from that particular plant. So this is one verification, that when the oscillation happened and how the plant responded. And you can also easily means when the actual PSS tuning is being carried out at the substation itself, then also you can do disturbance test by tripping of the line, keeping the PSS off and keeping the PSS on. Okay, so if the PSS is off, how the plant is responding. If the PSS is on, how the plant is responding. So like for tuning, we perform gain test for the stabilizer, a step test for the by changing the V reference of the excitation system, and by disturbance test by tripping one of the transmission line from that particular plant. So we keep the PSS on and off, and we check whether the with the PSS on, whether, and after the tuning of the PSS with the PSS on, whether the damping is improving or not. You can see that, you can easily monitor that. This black one is without PSS, then this one is with PSS, gray one. You can see that damping has significantly introduced. Earlier it was oscillating, magnitude was also high. Here also you can see that magnitude reduction is less, but the damping has improved significantly. Okay, so this is the disturbance test. So with this, we can easily monitor the performance of the PSS tuning that is being carried out, or the field testing that is being carried out with the PSS tuning when it is being implemented in the power plant itself. The third one is model validation. So model validation, I was informing that this when you do any kind of power system planning, so you need proper mathematical model of the various component in the power system, like the generator. Then you have loads also, transmission line also. The electro means the basically the electromechanical phenomena that are happening. You need to have higher order model, mathematical model of the various component which can contribute to the mechanical dynamics of the system. So like you have to properly model your excitation, properly model your governor. So these things are there. There are certain softwares are there through which you are doing this modeling, and then by putting the models, the parameters from the field for that particular plant, you need to check the system performance, whether the system is performing, or the dynamic behavior of the system for any event is whatever we are trying to look into the actual event, whether it is matching with the actual event or not. So this is what we call, we have a proper model, then you will be able to replicate any event in the system, and you will able to see that okay, the dynamic behavior of the system is also matching with the actual behavior that we have means during the event. So you're able to verify the model also, okay, the entire power. And when you do use a verified or validated model, then you are able to do take a very means a strong corrective action. You will be able to monitor, or you will be able to emulate any kind of event in the power system and check what is its root cause. So it is very important to have a very validated model in the power system. So this PMU data, if you have, let us say this generator is there, okay, and I want to evaluate how whether this generator has provided me this their turbine system parameters, governor system parameters. So we can do a model validation of this particular power plant by utilizing the synchrophasor data also. So what we try to do is that because means if you have any if there is a voltage or frequency change in this grid side, then the generator excitation, governor, everything will try to respond according to that. And when they try to respond, their active and reactive power correspondingly change. So what we try to do is, in the software side, for validating the model, we check for any actual event what is the frequency and voltage variation from the PMU. Let us say there is a tripping of one of the transmission line nearby to the network. So if we trip that particular line, then what is the how the voltage and this frequency of this particular power plant is going to change. Okay, and then we try to see, we model the same thing in the software, and we try to input this actual voltage and frequency. So, and based on that, we try to see how the active and reactive power is variation is there, and compare it with the actual active and reactive power observed through these devices, PMU devices. So this provides me, if the model is proper, then with that particular voltage and frequency change, the active and reactive power that this simulation should produce for this particular plant, it should match with the actual active and reactive power that we have recorded from the synchrophasor data. So these, means these are for validating the dynamic performance. You need to have this PMU data basically, because these requires very highly, means very whatever the data should be there, it should be able to capture the dynamic phenomena that is happening in the range of zero point 0.1 to 5 hertz range. And through the PMU data, it is already, I inform you that it is already available. So what we try to input in the software is the voltage and frequency, and we check the active and reactive power, and from this response of this unit in the simulation, how the active and reactive power is there, and based on that we compare it with the actual active and reactive power. So you can see that I have put voltage and simulated voltage is there, and it is replicating, the software is replicating the simulated voltage, the measured voltage, and measured voltage, and it is replicating it in the simulated voltage. So it's complete replication, and based on that it has provided a response of active power. And you can see the active power is also, there is a slight variation in the active and reactive power in the system. So, but however, the oscillation frequency, all these are quite matching. So this provides a validation of your, the model that you are utilizing. So this is one of the major application of synchrophasor data in compliance management, because right now the Indian electricity grid code has also introduced that, whatever the 2023 version, basically it has also asked the generator to supply the validated model, the validation, and based on the whatever the data they are going to provide, the system operators do check during event whether this whatever data they have provided, whether it is properly matching with the system. During any event, the system response, the unit response is properly matching with the particular event, and they try to use that particular event with the in the simulation software to validate the model, whether the model is providing the same response or not. So this helps in validating the model, providing the feedback to the generator that your model is not proper. Because if with improper model, you will be landing up in a lot of troubles, right? So this activity is also very important, and the PMU has also helped in this improving the dynamic modeling of the system also. The fourth one is inertia and frequency response model. Okay, so inertia is also very important to monitor in the system because of the increase in the inverter based generation and larger scale, means inverter based loads also are increasing, means the silicon load that we usually call, or the loads which are not responding with respect to the frequency. It is decoupled kind of thing from the system. So in that case, the contribution from different devices from inertia reduces, and the inertia is less, then the fall in the frequency will be high, rate of change of frequency will be more in the system. So lower inertia system provide a challenge to the grid operator. So the various small grids are facing, which have integrated lot amount of renewables. They are also facing a lot of inertia challenges. And for overcoming those inertia challenges, they are going for installation of synchronous condenser, basically, which provide the fault level as well as the inertial support to the system by utilizing external flywheels also. So this kind of means that's why this inertia monitoring is very important. So traditionally, this inertia monitoring was being carried out for any power system using the offline study. You model your governor, you model your generator and their inertia, load and their damping. All these are model, and then during the simulation, you do some tripping of the units and check how fast the frequency will fall. All these were done with the offline studies, or through the state estimator, dynamic state estimator. You can do this kind of a study, but with the gradual introduction of PMU, as I have informed you in the earlier slide, the frequency fall you are able to monitor very in a very high resolution pattern. Then that particular frequency fall can be utilized for rate of change of frequency for the center of inertia. Right? You have the frequency plot. If you try to find the initial rate of change of frequency by taking a slope at the initial frequency drop, then you will be able to use the power swing equation, because at the initial frequency drop, the impact of governor will not start, the impact of load will also be not be that much, because the fall in frequency is very less. So what you are going to get at that point of time is the combined response of the unit or the generator and the loads which are contributing to the inertia. So by utilizing that only, we can, if we have that initial rate of change of frequency, we can get the, using the swing equation, we can try to evaluate the inertia of the entire power system. So we can use that. activity. And we can check, these are basically, based on whatever the events happening on those events, we can check how the system inertia is varying in the during the particular time of day. So all these activities. Okay. So just there are ways of doing this inertia estimation, like large disturbance based or ambient data based inertia estimation. So what I am trying to go into the direction of large disturbance based inertia estimation, where you measure the response, find the rate of change of frequency for the center of inertia, or basically you see that means rather than, because entire whenever there is a fall in frequency, the electrodynamic phenomena is involved. So what will happen is that there will be certainly large drop in frequency at the near to the source of disturbance, and the drop in frequency, initial drop in frequency, will be slightly low. So there will be oscillation also happening. So you need to means remove these kind of variation, and you need to have a very proper means a center of inertia frequency basically. So after utilizing the wide, I mean, means you have a multiple PMUs placed in entire power system. In that case, what will happen is that you have a very geographically spaced means different locations frequency available for you, and based on that you can isolate that, okay, just removing this frequency which has higher oscillation, you will be able to see there is a smooth fall in frequency in certain of the PMU. So from there, you try to remove the noises and find a frequency plot which emulate your center of inertia frequency. So when you have that center of inertia frequency with yourself, then you will be able to utilize that particular frequency for calculation of the initial rate of change of frequency, initial Rokov. Because in the swing equation, you will find that you have, because I know as means in the system how much generation is lost, what is the total inertia that is available in the system, like MVA, how many units are coupled. So what is the total MVA available in the system at that point of time, the synchronous MVA basically, not all the MVA, only the synchronous part. So when we have the synchronous MVA, loss in the active power, you have the rate of change of frequency. By using the swing equation, you will be able to easily find the inertia of the system. So you can see that for one report is published on the Indian power system inertia estimation that is available in the public domain. You can go through that. So you can see, I have taken the plot from that. So you can see the inertia estimation, the Indian power system, it is roughly lying between 9 to 5 basically. So it is varying depending upon the system market, means how the system is evolving throughout, throughout the period. So in that way, and with the renewable penetration, you can say that if penetration of renewable is more, you see that the inertia is reducing. So this right now the inertia is having a very good, means we have very good rate of change of frequency for the Indian power system, and right now we are not facing any such kind of issues. But there are countries where the renewable penetration is quite more compared to the Indian power system. There they are facing a lot of challenges in that. So certainly the power system operator in India are already geared up for those kind of things, for this managing the this with managing the grid with when the grid inertia is going to reduce in the near future. So the voltage stability compliance. Okay, so you need to monitor. Means for voltage stability, you have already read about knee point voltage, PV curves basically, and P delta curves or VQ curves already. So with the PMUs, the conventional SCADA, you don't have directly the delta measured, right? The angular separation. You have to go with the state estimator and then calculate all these things. But with the PMU, you directly monitor these states in the system. So you can utilize directly for monitoring of the PV and P delta plot for different areas. So you can see that this is voltage, this is angular separation, and this is the active power flow. So you can see the PV trajectory, you can see the delta P delta trajectory, and you can verify that, okay, the whether the voltage stability is intact in the system or not, whether I am moving towards a unstable operation or not. So this can be directly monitored through the synchrophasor. So this compliance of the voltage stability compliance all can also be improved with the help of the synchrophasor. Then one thing is the voltage unbalance. So you can go through these definition. What is the voltage imbalance? What is the allowable limits? each in across the world, each countries have their own allowable limit of phase voltage and balance. Because we have a three phase system, certainly there will be some unbalance because the transmission lines transposition is there, and there will be methods through which these voltage and balance are trying to being controlled by balancing the loads, transposition of the transmission lines, different phases basically in the lines at different in certain after certain means length of the line. So through these are being tried to control. So however, the power system operator, it is very important for power system operator to manage, check whether the voltage imbalance is it is means in means it is violating the limits or it is not within the limits or not. So with the PMU data, we are having these three phase voltages of the system also and three phase current also. So with these the three phase voltages, we can easily check the voltage and balance in the system by comparing of the each voltage with a threshold value. And if it is exceeding threshold value, it indicates a potential issue. So let us see this one. Example is this one. So here you can see that the R phase is having a 14 kV difference from the rest of the two phases. So actually this was indicating that there can be a probable CVT or VT error what we are monitoring. There should not be any actual issue. Or if there is an actual issue, it will be observable through the nearby nodes also. So we are observing only in this particular node only that this particular imbalance was there. So after this replacing the CVT, we found that the R phase voltage has also come back. So this is also the voltage and balance compliance. If there is actually non-compliance is there, you can ask the utility to check that and improve on that, find the what are the remedial measures they can take. And otherwise, because this will be certainly going to impact the consumer level at the consumer level voltage also. And the last one is the like inverter based resources are increasing, so they have multiple compliances like LVRT, low voltage right through, HVRT, high voltage right through, LFRT, HFRT, all these are there. So with the help of the synchrophasor devices, you can also monitor the low voltage right through. Like means if you see this particular plot, the active power, there was a fault in the system. You can see that the generation has reduced, but it has not went down to zero, because when there is a fault in system, the at that time the reactive power control tech means dominates, and in that case they will be putting more reactive power into the system. Active power get reduced because inverter has its own limitation on the current side. So if you increase the reactive power, you have to reduce the active power, and when the fault is getting clear, after immediately you have to again bring back the active power into back into the system. So this low voltage right through, high voltage right through, all these compliance can also be checked from the synchrophasor devices that are installed at the these inverter based resources substation itself, or the transmission line from which these are getting evacuated. So this all this monitoring can also be done through the synchrophasor. And the last one is the protection validation. So you can see that because the protection is operating, let us say there is a fault. In Indian standard, the minimum fault clearance time is 100 millisecond at HV level. If you go to the 220 kV level and below, it is 160 millisecond. Okay, so 100 millisecond to 160 millisecond is the response that you need to clear the fault through your main protection system itself. So if you find that if there is, because 100 and to 160, roughly if you divide it by 25, you will have a one sample of data for, let us say it is 160, then you can have 4 to 5 sample of data for that particular fault. And subsequent to that for means other kind of thing, other kind of protection, like which are slightly delayed in nature, or which have some inherent means means directional earth fault is there. Directional earth fault has certain limitation on the side that it will operate after certain point of time. So this is a delayed kind of thing, it is not instantaneous in nature in generally. So in that case, you will be able to monitor those responses, whether those responses are validated or not validated. Like you can see that one of the example is there is a delayed fault clearance over here. So you can see that you can easily monitor through the transmission line PMU that its volt current of that particular line is monitored through which where the fault was not getting cleared. So you can see how the fault current is reducing with tripping of each of the lines. So this is how whether the main and backup protection system is properly operating, Then rate of change of frequency relay is also there, so that whether it is operating correctly or not. Then there is a synchro check relay settings are there. If the synchro check relay is properly operating, whether the synchronization is happening at the very minimum, the angular difference, so that there should not be any large jerk. If the synchronization not happening properly, you can see that if the synchronization happening at 30 hertz, you can see a large swing can be observed in the system also. So this is some of the example of this protection validation. So overall, the summary is that the synchrophasor with its high resolution data has provided a paradigm shift in the operational activity as well as the compliance monitoring, which is very important for the grid operation, basically, to see whether the all the equipments are in the compliance of their proper standards or not. Because most of the compliance, means during the dynamic state, you need to focus on whatever is already inbuilt in the system. They should properly respond so that your stability is improved during the fault or any event, because at that time operator directly cannot do anything, because these are happening in milliseconds. Okay, so that time you rely on those automations, basically whatever the automated actions are there. So that's why for those automated action, this compliance monitoring through the PMU is very useful for us, for providing that, okay, the whether the equipment has operated properly or not properly, and then further fine tuning it, taking corrective action on that. So there is with this monitoring of the compliance through the PMU, there is a significant improvement in the system reliability and security also. And we keep on working on the various new use cases through which they're capturing all these and trying to improve upon the system operation activities and compliance monitoring activities.